Welcome to Lecture 7, the first lecture video on electricity and magnetism for Physics 4B. With this lecture, we are studying first of the topics that this class is really about, the first complete theory of physics. By the way, depending on the semester, you may be seeing this lecture immediately after a mechanics review and a brief intro to thermal physics, lectures 1 and 2. Not to worry, we will return to thermodynamics at the end of the semester, and nothing we cover in electricity and magnetism fundamentally depends on the thermodynamics content. So, we start this lecture with a brief introduction to electricity using pieces of cellophane tape to demonstrate static electricity phenomena. And we jump right into introduction of Coulomb's Law, which describes the force between electric charges. While we will defer heavier calculations until a later lecture, as a brief demonstration of calculus approaches you may be called to use, we calculate the electric force between an extended body of charge and a point charge. We also introduce the idea of electric field that we will make more extensive use of in future lectures. And we review some of the mathematical details involving vectors that you may have covered in your earlier classes, Physics 4A and the prerequisite math courses. This is a long lecture, so we will cover additional examples utilizing the electric field concept and direct integration of electric field contribution from extended bodies in a separate lecture. So, welcome back. So, starting with today, we are moving on to an entirely new topic. We are now entering the main part of Physics 4B. The thermodynamics, it had to be stuck somewhere in the 3-semester sequence. And in Peralta, we do it in this class. You will find that in different schools, they do it in different semesters. So this is like the first day of class, except, 4 weeks later. We are moving on to electricity, and I hope many of you have some level of intuition for electricity, as in, you've seen demos like this. It's a simple thing to demonstrate. I have, bunch of pieces of paper that's lying somewhere here, and I can pick up a balloon and pick up those pieces of paper without touching them, or I would eventually touch them, but sort of lift them up without directly touching them. Let's see if it'll work. Yeah, you've seen this before, right? You played with something like this as a child. So. In Physics 4A, I spent a whole half a lecture trying to tell you that all the forces that you deal with in Physics 4A, other than gravity, are contact forces. Now, that turns out to be a lie. So even what you feel as contact force is actually a non-contact force. They'll eventually be described as an electrostatic force. So when you look at electrostatic force as one of the 4 fundamental forces of nature, it's a non-contact force. I can exert force on those pieces of paper without ever touching them. So what we are going to do is we are going to, in the next 4.5 weeks, what we are spending time is we are spending time first going over describing what this electric force is like. That's half a lecture today. And what the majority of the time will be is developing some mathematical tools for dealing with this electrical force. So let me just start out with some background material that I hope many of you are familiar with, but maybe it's like with thermodynamics. Because I'm not supposed to assume you have taken any science classes before this, I want to make sure everyone's on the same page. So let me write this electricity background material. It's something that you hopefully have heard of before, but if you haven't, then now you are hearing about it. So when you talk about electricity, like that interaction between the balloon and the pieces of paper, the important part of the description is how this interaction happens. And so the scientists in the, well, Benjamin Franklin in the 18th century discovered that the way this interaction happens is through what we now call electric charge. That when you look at these interactions, the way we describe them is with the electric charges. Say that the balloon has positive charge, and this paper has somehow negative charge, and it's the interaction between these electric charges that's responsible for all the electrical phenomena that you see. Okay? How many here haven't heard of electric charges before today? Everyone has heard of it. Good. So there are some properties of electric charges that we should go over. I mean, I hope all of you have heard of this before, but if not, now is the time that you should know about it. So it comes in two different kinds, or there are two electric charges. I don't want to say kinds or types because they are the same type. They just have two opposite signs. So there's the positive charge and there's the negative charge. And actually, I thought we would go through a simple physical demonstration to illustrate why we think there should be two different signs of electric charge. So I have this cellophane tape, which worked well. Last few times I've done this. So let me pass them out. So this is the exercise I want you to do. I mean, so you guys already have some experience dealing with, I don't know, what do they call it? I don't remember the name. You use it in kitchen, like a plastic transparent cover. Saran wrap, yeah. You have some experience with saran wrap. When you unroll it, if you're not careful, it'll just stick to other things. The cellophane tape behaves in a similar way. So this is what I want you to, series of exercises I want you to go through. I want you to have some length of the tape, rolled out from the tape, and try not to touch anything with it. And try to avoid touching anything else. And with these two tapes, having the non-sticky side facing each other so that they don't actually stick to each other, try bringing them closer and see if you see any indication of an interaction between them. So I'll give you some time to try it out. There's a second set of exercise I want you to do. So once everyone has tape, that might not be long enough. This is what I want you to do. Lay down one of the tape, sticky side down on the table. Make sure to leave some length for you to be able to handle it with. So don't, tape it all the way down. You're going to, untape it soon. So make sure you have a little bit of that. And lay down the second tape right on top of it. But, before we do this, you guys saw the interaction between the two tapes, right? Were they repulsive, attractive? Repulsive? Okay, good. So now what we are doing is stick the tape on top of each other on the table, leave a little bit of length, and after having stuck them on the table, I want you to peel it off one at a time. Peel off one and peel off the other. Please be careful so that it doesn't touch your, run up to your hand. Now try to bring the two tapes together, non-sticky side together. So Crystal, what kind of interaction are you seeing? They are now attractive, right? Yeah, in fact, if anything, the attraction is stronger than the repulsion ever was. So this is a very simple example of electric phenomena. And our goal of trying to describe electricity now is we want to come up with a description that would explain both of these things. But with the electric force, the other non-contact force, what you're saying is that it can be attractive and it can be repulsive. And in this particular case, with the same two objects, you could arrange them in such a way that they were repulsive initially, but then after some interaction, they are now attractive. So the description using electric charge is a way to describe exactly how that might be happening. So to So that's why we start out with the description of a positive and negative charge. With the masses, there's only one mass, or one type of mass, positive masses. I can't even imagine what negative masses are. So I guess, yeah, I can imagine what negative masses are, at least in vacuum. So with these positive and negative charges, now you have more of more fun combinations in interaction. As in, you can have, let me just describe all those combinations. You can have a positive charge interacting with another positive charge. You can have a negative charge interacting with another negative charge. Or now you can mix them up. You can have a positive charge interacting with a negative charge, or negative charge with a positive charge. Now, I think many of you know this rule already, but let's go over just to be sure. When you have two positive charges interacting or two negative charges interacting, do you know if it should be repulsive or attractive interaction? Repulsive, you guys might have seen it in science class. Or this sometimes goes by the phrase, likes repel. What about in these two scenarios? Either positive charge interacting with a negative or negative with a positive. Should be attractive, yeah. It goes by the phrase, opposites attract. I mean, you know, just like with the statement regarding Newton's third law, sometimes people take this and mean it to make it mean something entirely different. But at least with electric charges, so the like charges, two positive charges will repel each other, and two negative charges will repel each other. And the opposite, a positive charge will attract a negative charge will attract a positive charge. So this is a way of trying to explain what we just saw. Let's see if these rules make sense with what you just saw. So what you just did, initially you started out by rolling out a piece of tape, or two pieces of tape rather. You have a roll of tape here, and what you've done is you've taken a piece, so one piece here, and you've taken another piece earlier. So when you look at these two tapes, two pieces of tape, do you think they will have the same charge or different charge? Like they got rolled out the same way, right? You have no reason to think that they would have a different charge, unless, you know, this something weird going on is with the tape. So because they are being both rolled out at the same way, you have no reason to think they wouldn't have the same charge. And the interaction you see between them, is it consistent with them having the same charge? Right? Repulsion, at least according to this rule we are trying to say. Now, do you know enough to say whether they both have positive charge or they both have negative charge? Not really. They could both be positive, they could both be negative, and they would both show repulsion. And in fact, here's the thing about the signs of electric charge. It's arbitrarily assigned. And in fact, when we start doing electric circuits, you will realize that the way we have the signs assigned is very inconvenient. You can blame Benjamin Franklin for that. But it's an arbitrary assignment. And it comes down to what we can tell are whether these are same or opposite charges. So for now, let me just label them as positive. I don't actually know if they will be positive charge, but let's say they have some amount of positive charges. Sorry, I drew too much. They have some amount of positive charge, but not too much, because we saw that, especially compared to the attraction that you will see soon, that the repulsion you see now is not that strong. Yeah? And the next part of what we did is we put these two pieces of tape together. So here's the bottom piece of the tape, and here's the upper piece of the tape, and we peeled off one at a time. And let me just do it again. All of you have done this once, but let me do it again. I can't do it on my table because last semester I tried it and it didn't work. It only works on these tables. Something about the property of table matters. So I'm not saying that this happens all the time. I'm just saying, this happens in this specific situation, and that's the explanation we are coming up with for it. So after having pulled this off, you see that these two pieces of tape now attract each other. So if you're trying to make sense of this rule, what do we now need to be able to say? To say that, oh, these two pieces of tape now attract each other. Like, what do we need to be able to say about the charges of each of the tape? So the tape that's up here and the tape that's down here, what do we need to be able to say? Yeah, the one is positive and one is negative. They somehow have opposite charges. Let's say, all right, let's say this has a positive charge. And let's say the bottom one ended up with a negative charge. Then here's the question that you would end up asking. Where did the negative charges show up from? There were no negative charges anywhere here. Like, where did they come from?
The table?
It could have come from the table, which is why, I guess it could have come from the table. I want to try to, wonder if I can do it this way.
Can you do it on the board? Or?
No, I want to try it this way. So I'm trying to touch the table as little as possible. So I haven't actually tried this before, so I don't know if this will work or not. Let me just have the tapes touching each other, without touching anything else. So it's just tape on tape. I wish I had tried this before, but until Pedro suggested it, I hadn't thought of it. Let me just fold this over so that I can unpeel it later. So it's tape on tape. All right, and let me peel them from each other. Okay, they're peeled. They attract. So the table wasn't necessary. All right, so where did the negative charge come from? From the other tape. So what this is showing is maybe a transfer of charges. So in this picture, you could say it this way. So I drew 4 charges for each of them. So 1, 2, 3, 4, 1, 2, 3, 4 positive charge. But maybe the real picture is more complicated than this. Instead of these having these 4 charges, this is more like a 4 net positive charge. As in, within this tape, there's a collection of positive and negative, positive and negative, positive and negative. Sorry. Let me just do it for only one of them. I imagine similar picture for the other tape, but so since positive and negative will cancel each other out, you wouldn't know if this had both positive and negative charges. It just had an excess of positive charges or a net positive charge. And in the process of peeling one of the tapes over, the process might involve all these negative charges that I have not drawn being transferred over to the other tape. That would result in the other tape having a net negative charge, and the top tape ending with an even greater excess of positive charge. Does all of this kind of make sense? I mean, most of you have a normal science education background. So what I'm trying to say is that this is the description of how we describe charges interacting, and sort of this makes sense here. And here, I've actually introduced an idea without directly referring to it. It's something that's so intuitive to many of us that some semesters I've actually forgotten to mention it. So the idea that you are seeing illustrated here is what might be called conservation of charge. Does this sound like a strange concept to people, or it's something that you would have assumed? Most of the people who know something about science is already familiar with the conservation of mass, conservation of energy. So the idea that charges are conserved seems sort of natural, right? As natural as like if I have some piece of paper, then this piece of paper will sort of like, it won't simply disappear. It can change its form. I can burn it and turn it into carbon dioxide, but what's here can't simply disappear. And with the conservation of charge, it's even more fundamental than conservation of pieces of paper, because pieces of paper can change its form. Turns out these charges that we are referring to, they are properties of the very elementary structure of matter. So whatever charge there are, the net charge will always remain the same. You can transfer some negative charge from one object to the other so that it results in separation of charges, positive and negative, and you can see them interacting. But when you look at the total amount of charge, negative charges cannot simply disappear, and the same thing with the positive charge. So let's try to be a little bit more quantitative. So you've seen the attraction over a distance of these pieces of paper, and you've seen how charge could transfer from one object to the other using the tape. But all these are these are qualitative descriptions, as in this is something that you have seen in your, whenever you are taking your basic science class. I think a middle school is actually correct description here. So you have taken way more math since then. You know algebra, you know trigonometry, you know calculus. And so, all of that additional knowledge must come with some additional benefit. And Coulomb's law starts the way we are going to treat electricity in this class. So I want to do this as a demo. So these two are pith balls. They are very light styrofoam balls that has a little bit of a silver coating on top. And now what I'm going to do is I'm going to bring a rod, which hopefully has some charge on it, near these balls. Wow, it doesn't have any charge on it. I thought this is the right material. The pith balls are charged with a half turn of HB Genecon. You can see the pith balls getting near each other over time. It's because the sharp corners of the setup leaks the charge. I'll charge it again with another half turn. And the separation illustrates the electrostatic repulsion. Now I'm trying to maintain the highest possible voltage and the amount of charge on the pith ball. This is limited at some dynamic equilibrium where amount of charge generated equals the charge lost. With those pith balls, when you put on some amount of charge, you get something that looks like this. Two pith balls, they will separate. And you can say, all right, they have some amount of charge here. Let's call it plus Q. And would this also be positive charge if they're separating? Yes, because they're repelling, right? Positive Q. So if you have a way of figuring out how much charge each of these had, then this becomes a way of being able to estimate what is the quantitative relationship between the electric charge, the object that it's applying force on, and any other sort of parameters that are there. So with these pieces of paper and the balloon, by rubbing, let's say I put in some amount of charge on this balloon, and whatever that amount is, it's not changing. And what do you see changing between the balloon and the pieces of paper? that either makes it, not that much clear that there's any interaction between them, versus there's now clearly interaction between them. Like, what's the one variable that that seems to affect the amount of force between the paper and the balloon? Distance, right? Yeah. So when it's closer, it exerts greater amount of force. Oh, sorry, charge is selected. When it's closer, it exerts greater amount of force. When it's farther away, it doesn't exert as much amount of force. So all of this should seem intuitive, right? And people have done experiments with setups like this before. And in the, this has got to be early 19th century, maybe a little bit before. So the result of all that experimentation is what we call Coulomb's Law. So Coulomb's Law relates force due to electric charge. So it relates electric force to the electric charges. And we can actually guess some aspect of this Coulomb's Law. We are going to say, at least to start, we'll try to say this electric force is proportional to some combination of quantities. So, when you look at here, what do you think electric force would be if there was no charge at all? Then 0, right? And as you increase the amount of charge, can you imagine electric force increasing? Right? Okay. So what I want to say is that this electric force is, to start out with, proportional to the amount of charge. Right? Now, when you start thinking about the amount of charge, it actually, it's not just one charge that you are thinking of. Imagine that one pith ball had an electric charge, but the other pith ball didn't. Will there still be electrical interaction? So it's, yeah, and it turns out, so the electric force is always force between two charges. So if this is 0 charge at all, then no electrical interaction. So they both need to have some amount of charge. So electric force is proportional to, not to one charge, not to the other charge alone, but it's proportional to product of the two charges. So more charge collectively means more force. And you guys saw the dependence of electric force on distance. So we are going to come up with some functional form that makes the force go down as the distance increases. Any guesses what that form might be? We're just guessing. People had to do experiments to find this. I mean, you might know this from your earlier science class, but, Yeah, you're saying K right now, so you're just telling me what Coulomb's law is. I want to get to that, because unless you have it memorized to start out with, I want to make sure that this law makes sense to you. Having it memorized and having it make sense to you is two different things. So we took care of the charge portion, and we are going to take care of the distance portion, and we are going to eventually move on to the constant between them. So, so how do you think it should, just taking a guess, not memorize the version of Coulomb's law, how should it depend on the distance? So if we put the distance on the denominator, that's one way of having it, having the force go down as distance increases. So, you might guess this as the form, proportional to product of charges and inversely proportional to the distance. Turns out experimentally, it's a distance squared. So this is the part that you can't quite guess. You have to know this experimentally. Right? Now, in all the laws of physics, the goal really isn't to remain at this proportionality relationship. We really want to get to some expression where we can say this force is equal to some set of expressions here. But when you look at it, there's one major obstacle here. Anybody here know what the major obstacle here is? This, by the way, is why we emphasize dimensional analysis so much in Physics 4A. But it's not until physics 4C that you see true value of dimensional analysis. Units are all wrong. Here, the units are newtons. Or, it's force, right? So in the basic SI units, this newtons would be kilogram meter per second squared. Anybody here know what the units on the right-hand side are? Yeah, it actually gets a little bit complicated because we have these charges. Anybody here know how to express a unit of charge in terms of kilograms, meters, and seconds? Turns out within the unit system of a SI system, you can't. There are unit systems where you can. It's called Gaussian units or sometimes CGS units, where you do define unit of charge in terms of these, but they involve ugly square roots or whatever. We're just going to stick to SI units. And in SI unit system, we actually define a new unit just for charges. So even though it's still totally true that three quantities define the basic way of measuring things in physics, to make things more convenient, we're going to introduce a unit of Coulomb. So the unit of charge, we name it after Coulomb, who did a lot of work. So these charges come in units of Coulomb, or capital C. So the units on the right-hand side so far are this. It's a Coulomb squared per meter squared. Do these look like the same units? Nope, not at all. So how do we fix this so that we can say the left-hand side is equal to the right-hand side? Maybe let me build your intuition this way. Where else have you seen a similar expression before? You have force on one side, and on the right-hand side is an expression that describes how that force can be obtained. And actually, a lot of these have a very similar feature to that other equation or law that you might have seen before. Newton's law of universal gravitation. So as a reminder, this is what it looked like. Newton's law of universal gravitation, force on the left-hand side. On the right-hand side, it's proportional to the product of masses. Mass 1 times mass 2 over distance squared. So when you look at the units here, you face similar problem. On the left-hand side is unit of newtons. On the right-hand side is unit of kilograms squared per meter squared. How do we fix this? Yeah, there's a constant, gravitational constant G. And this constant, it does two things. One, it gives you the exactly correct unit so that you can now say this equality. So this G, without knowing anything else, you can say this G must have these units. It must have unit of Newton times meter squared per kilogram squared. So Crystal, this is how we cancel out the unnecessary units here. But we do it by including it into this constant. This is the systematic way of doing it. And this G has a very particular value. You can look it up in the textbook. It's one of the things about G is it's a very small value, right? So because Coulomb's law really reminds us of Newton's law, in fact, it's in this inverse square relationship where it really reminds us of Newton's law. We are going to take the similar approach. So we are going to introduce a physical constant here that for the time being, we are going to call it K. We are going to call this K, not to be confused with the Boltzmann constant. So we need a constant here to make the units come out right and to have the correct number. So what should the unit of K be? Yeah, I need the newtons. Anything else? Yeah, meter squared per coulomb squared. Yeah. So this is how we get rid of this unneeded or unwanted unit of coulombs. We do it not arbitrarily, but by including into this physical constant. People have done experiments to find the value of this constant experimentally. We can plug in numbers and just have a sense of how big or small this number is. So let me plug in the numbers. This is 1 over 4 pi times epsilon naught, about 9 times 10 to the minus 12. 9 times 10 to the minus 12. And let me be careful with the units here. Coulomb squared per Newton meter squared. So when you work all of this out, 4 pi is about 12. 12 times 9, that sounds like about 100. So 100 times 10 to minus 12, that's about 10 to minus 10. So this is going to be approximately 10 to the 10. And working at the unit, it's 10 to the 10 times Newton times meter squared per Coulomb squared. Is the unit what we expected? Yes, I mean, it should work. And so the number that goes with that unit is approximately 10 to 10. I think if you do more exact calculation, it's like 9 times 10 to the 9 or something like that. Is that a small number or a big number? It's a big number. That's one of the features of electricity, that this constant that occurs here, it's going to be a pretty big number. So when you look at charges, so we introduced the Coulomb as the basic unit. You will find that 1 Coulomb is an unreasonably large amount of charge. We'll look at it in some of the problems, but 1 Coulomb is a really huge amount of charge. Actually, let's do it now. We can do this calculation with this example here. So, hi. In this video, we'll look at one of your homework questions. So this question from your homework deals with electric forces, and this is an excellent opportunity to review some of the problem-solving techniques that you should have learned in Physics 4A, but maybe it's been a while ago, or maybe you never learned it properly. So let me use this opportunity to review the techniques for solving force problems. So let's review what information is given. 2 small balls, each of some mass, are attached to some threads of some length, which are then tied to the same point, and we are given the angle that the thread makes with the vertical, and the balls are given some charge Q, and they hang like this. And the question asks for what is the magnitude of the charge. Alright, so this is a force problem. Depending on how experienced you are at solving them, you can mentally check off as you review this information that this problem is completely determined, that you are given enough information in the problem to be able to figure out the magnitude of the charge. Now, if you don't have as much practice, then let's go through the steps that we go through in Physics 4A. This is what we call standard strategy. It's a 4-step strategy. Let me outline it for those of you who might have forgotten it. So I'm going to be brief in my description of each of the 4 steps because I want to keep this video short. But please understand it is meant to be a shorthand for all the considerations and things that go into it. So the first step is you draw a free body diagram. The second step is you define coordinate axis. The third step is you break down forces that you have from drawing free body diagram into components. And the fourth and final step is you write down Newton's second law equation. Now, what you should realize at this point is that you are not actually done solving the question, because this standard strategy isn't meant to be something that spits out the answer. It's meant to take you to a place where you have a system of equations, so now you can apply math for the remainder of the question and solve for whatever quantity is asked for. So that's what we are going to apply to this problem also. So let me start out with step 1, drawing free body diagram. I'm going to pick one of the 2 charges to draw the force diagram of, let me pick the charge on the right. So I try to keep my free body diagrams as simple as possible. So most objects get represented with a dot. And my job for the next couple minutes is to draw all the forces on this dot. I have couple rules to keep me on task here. The most important rule is that I only draw the forces as needed. It keeps me from identifying forces that don't exist. So here, the force to start out with is gravity, the weight. It's sort of ever present when you're on Earth. Once you draw the weight, then questions start popping up. Why isn't this ball accelerating downward? Well, it's because it's tied to a string. So there must be tension force then. Tension force goes in the same direction as the string, so let me draw that. Going to exaggerate the angle a little bit. And once I draw the tension and weight force, then there's still questions remaining. Why isn't the ball accelerating to the left? And this is where electrostatics actually now comes in. It's because there's a Coulomb repulsion force between the two balls, which is pointing to the right for the ball on the right. So now my free body diagram looks complete. All the forces are identified there, and the diagram I've drawn is consistent with the fact that the ball is not accelerating. All right, now step number 2, I need to define the axis. We usually define the axis so that one of the two axes is parallel to the acceleration. Here, since we have zero acceleration, it sort of makes sense to pick the axis that kind of lines up with the forces, so that most forces are either along the x direction or the y direction. This makes our job in step number 3 easier. We need to break down forces into components. So here, gravity and the electric force are already along one of the axes, so no components to deal with. But the tension force is in some oblique direction, so we have to divide it up into the y component and the x component. And this is also the step where it's useful to label all the angles and work out some expression for the components also. So the angle given in the problem is this angle theta here, and staring at the geometry, that should be the same angle as this theta, which gives us the expressions for the x component of tension and the y component of tension. All right, now we are ready for step number 4, writing down Newton's second law equations. So the thing to remember here is we need to write down Newton's second law equations for each axis and each object. So we need to write it down for the x component and for the y component. So it looks like we have two forces in each of the components. So let me write it down. The electric force minus the x component of tension, Tx or T sine theta, is equal to 0, mass times acceleration. And the y component of forces, the y component of tension, T cosine theta, minus mg is equal to also 0, mass times acceleration. So here we have all the information we need to solve for the electric force. So let's do that. We won't quite be done because the question is asking for the electric force. But I think that's a good intermediate step where that's the question you could have been asked even in physics 4a. So I'm going to solve equation 2 for tension. And when you plug it into equation 1 to eliminate tension, you get the electric force is mg tangent theta. And we have numerical values for every quantity here, so we can calculate what electric force is. Unfortunately, that's not the question. The question is, what is the magnitude of Q? So this is where we now have to use our knowledge of electrostatics to relate to the charge. So you remember Coulomb's law? This electrostatic force should be Coulomb's constant times the product of charges, or in this case Q squared, divided by the distance squared. Looks like we don't quite have distance information given directly to us. We need to figure it out from geometry, which is, I guess, what this length is here for. So we can figure out the length of this leg here. We have a right triangle. So this leg is L sine theta. So the overall distance between the two charges should be 2L sine theta. Alright, plug in all that information in. This is the equation we get. mg tangent theta is equal to Coulomb's constant times q squared divided by 4L squared sine squared theta. Okay, let's solve it for q. Alright, so this is q. We can probably simplify it more, but since we have all the numerical values and we're not planning on doing anything with it, it seems like there's no real payoff here. So let me just plug in some numbers to Wolfram alpha to get a sense of what a typical amount of charge value is for a realistic situation like this. So let me type in the formula here. Square root of mass 8.5 grams times g 9.8 meter per second squared times tangent of the angle 5 degrees times 4 times the length 90 centimeter squared times sine, I'm gonna be squaring it, sine of the angle 5 degrees squared, all of that divided by the Coulomb constant, and this wraps up the square root. So this should give me a value in unit of Coulomb or probably microcoulomb, possibly nanocoulomb. Oops, Japanese 10. Let me spell this out. So this is seconds squared, and I think the rest should be fine. Let's check. Yeah, so it should give me a number in ampere times a second or coulomb, or in nanocoulombs. 141 nanocoulomb, or in microcoulomb 0.141 microcoulomb. So as I was saying earlier, 1 coulomb is an unreasonably large amount of charge. In most macroscopic situations, when you have a setup like this, two pith balls separated by some number of centimeters, it's gonna be dealing with the microcoulombs of charge. So that's it for this example. In other lectures, we'll look more at the mathematical properties of Coulomb's law. Bye. So with Coulomb's law, eventually you have to worry about interaction between an extended charge distribution. And to keep it simple for now, extended charge distribution and a point charge. So let me use the remaining time today to set up the paradigm for dealing with a situation like that. And we are going to talk about that more on Thursday, how we would actually do that. So let me set up this situation, the situation that exactly I was describing. Let's say I have some rod that's charged up, and let me make it easy for myself. Let's say it's uniformly charged, meaning in this segment, there's as much charge as there's charge on this segment. And I want to be able to describe how much force is on this ball from this rod. So I have a uniformly charged rod of, let's say it contains some amount of charge, capital Q. And it's going to be interacting with a point charge here, which has some amount of charge, lowercase q. And let me finish the geometrical description of the setup. Let's say they are separated by distance d, and the length of the rod, I feel like that's going to be important, is length L. So suppose someone asks you for what is the force on this charge. How do you answer that? How do you answer? Can I just say, well, force on that electric charge is equal to K times product of the charges divided by distance squared. Can I say this? I mean, the setup of the question is, if that were the answer, then I wouldn't need the 15 minutes, right? So what's wrong with this expression? The distance. Yeah, you don't exactly know. So, when I say d here, I am saying, all right, so this is the distance that matters. Well, that's true for some portion of the charge, but there's this charge here that's, at d plus L. So then your first guess might be, well, why don't we use the average distance? Do it to the midpoint, say d plus L over 2. And there are some special situations where this works. And the example in physics 4a was when you're dealing with the two spherical masses, then you could use the distance between the centers. And that worked out exactly mathematically. When you take things that are more general, like this shape here, using something like this, that doesn't work anymore. So you have to fall back to the basics. You have to you have to use the approach that physicists use whenever we run into a problem like this. We would like a value of distance to use, but there's no one value of distance I can use. So what have you seen me do when faced with the situations like that before? Integrate, but that's skipping a step. Integrate means to add things together. What am I adding together? Yeah, so the very first step I'm going to do is I'm going to break up the problem. I'm going to imagine breaking up this entire piece of rod into tiny little pieces of rod. I'm not actually doing it. I'm just imagining that this is made up of very small, tiny pieces of rod. It's too many to draw, so let me just draw a few here. And what you have to imagine is that each segment of rod here, it's a very, very, very tiny piece. I can maybe characterize it with some infinitesimal length, dx. What I can say about this segment of the rod is I know how far this is away from the charge. This is as far away from the charge as the distance x, which is going to range from d to d plus L. Okay? So there's a reason I want to walk you through these steps. Because when you say integrate, usually the biggest problem you will run into is what are you integrating? And so in a problem like this, the most difficult step is actually setting up the integral. With some exceptions, the integral itself is actually not that hard. So let me go through, walk you through this thought process for setting up of the integral. So what I'm telling myself right now is I don't know how to handle the whole rod, but I do know how to handle a small section of a rod. So let me write down an expression for that. So what I'm saying with this small section is that I don't know how to get the whole electric force, but I'm going to be able to get small contribution to the electric force that's coming from this small section of the rod. So I can say that small contribution to the electric force still follows the Coulomb's law. That's K times the amount of point charge times amount of charge that's in this segment of the rod. So let me call that dq for now. It's a small amount of charge in the small segment. Divided by x squared. So this is what I want to integrate. When I integrate this over the entire rod, when I do that, then I'm going to get the whole force. There's a little bit of a tiny difficulty you have to work through first. Anybody see that tiny difficulty that you have to work through inside of this integral? What's the variable that's changing inside the integral? Q is not really a variable. I mean, this is not, but even the big charge Q, like when you look at the small segment, the amount of charge within that is not really what's changing. right? So so dq, this is a symbolic representation for something that you are going to need to replace. So what's actually changing inside of this integral? Yeah, as you go over the rod, the variable that's changing is x. So what you need to do is you need to express this dq in terms of x. Somebody tell me how to do it in next 10 seconds or so. Or in the interest of time, I have to do it. So you will see this often enough, so let me just do it this time. So what I'm going to do is I'm going to introduce the idea of linear charge density. As in, okay, that's the total amount of charge. This is the length. I'm going to say linear charge density is Q over L. That's however much charge is in a unit length. So with the introduction of this idea of some kind of density, what I can say is that this small amount of charge dq, I can say that small amount of charge is equal to the density times the small length that we are dealing with there. Yeah? Does this expression make sense to everyone? Yeah. So I'm going to substitute this in, and then it looks like this. I'm integrating over the rod, k times q times lambda times dx over x squared. Now this is beginning to look like an integral I know how to do. So I'm going to integrate over the rod, and that means I'm going from x equals d to x equals d plus L. So x goes from d to d plus L. Good? Everyone okay with how this integral was set up? Yeah, let me finish it up. So I'm going to pull out everything that's constant. K, Q, lambda. So I have K, Q, lambda. The only thing that's remaining is dx over x squared. What's the antiderivative of that? What's the antiderivative of 1 over x squared?
Isn't it ln of x?
Nope, you skipped one. Okay, let me rewrite it in a format that might be more easier. X to the power of minus 2. Yeah. Minus 1 over x. If you're not sure, take this, take the derivative of it. You should get this back. I'm evaluating it the limit. X is equal to d to equal to d plus L. So let me plug all those in. This time, I usually skip steps here, but let me not skip here because I want to make sure that this minus sign is supposed to be there. Is equal to k q lambda times the upper limit minus 1 over d plus L minus minus or plus the lower limit 1 over d. Is this value positive as I'm kind of expecting it to be? Yeah, it's minus over 1 over bigger number plus 1 over smaller number. So, if you wanted to really convince yourself, you can rewrite this as, let me do this. So d times, on the denominator, d times d plus L, and on the numerator, it'll be minus d plus L, so these cancel, so you get just L, the numerator. So, or all of this is equal to k, q, lambda, let me use this, times L over d times d plus L. And hopefully the units work out. This is the force on charge Q. Yep. Any questions? All right, I'm kind of out of time, but let me ask you this one last question. What if someone turned this question around? Instead of asking for the force on the small charge here, somebody turned this question around and asked you for, well, what is going to be the force, electric force on the rod? Do you believe that the rod will also feel an electric force? Okay, so how do we find this in the next minus 40 seconds? There's a so you could go through this entire set of steps all over again to find it, or there's a really quick shortcut to find this right away. Just sign me the law of nature that tells you that this has to be true. Which law? You said reaction. Which law does it come out of? Yeah, Newton's third law. So here, what we can say is that because of Newton's third law, when there's an action force, there is going to be reaction force. So this reaction force is going to be equal in magnitude. So Newton's third law, it's a universal law. It holds for every other law of nature that describes forces. Electric force is consistent with the Newton's third law of nature, motion. So when we find this as the action force, then, well, the reaction force, this is the reaction force. It's going to be equal in magnitude to the action force. So if somebody asks you for this, you don't have to go through the whole series of calculation. You can just, I know the action force, so the reaction force must be that.
So the law that we are going to write down, it's the distillation of that experiment done by other people hundreds of years ago. And in this class, we call that law Coulomb's Law. And it's one of those things that can't be derived. You have to, you just have to know it, or you have to figure it out through experiments. And once you figure it out, then the form of Coulomb's Law, let me just write down the final form, which will look like this. The electrostatic or electric force is given by some constant times the product of charges, Q1 times Q2. For some reason, we use letter Q for charges. I don't think I ever got the explanation why. Divided by distance squared. And for distance, for some reason, we use letter R. And it's a vector quantity. I need a way to indicate direction, and that should be R hat. So this is Coulomb's law. In one single line, it contains quite a bit of information about electricity. The biggest thing would be that this is an inverse square law. It makes it so that the strength of the electric force is weaker for objects that are farther apart, and it's stronger for objects that are closer together. And so that's the consequence of the inverse square law. When R is small, the force is great. When R is large, the force is small. And you have actually seen an inverse square law before. In physics 4a, you have seen the gravitational force, not the mg version. That's the approximate version that's usable when you are near the surface of the Earth. For the more general expression, universal law of gravitation, you have seen this. G times product of masses divided by distance squared. And in terms of mathematical form, electrostatic force, Coulomb's law is very similar to the Newton's law of universal gravitation. They are both the inverse square laws, and they are both conservative and so on. So that's the first piece of information that's embedded in this one line of equation telling you about Coulomb's law. It tells you the other stuff as well that you might have guessed, even if no one told you, that it depends on the strength of this force depends on the magnitude of the pair of charges that are interacting. So if you have two charges that, if even one of them has no charge, then there's no force between them. For there to be electric force between them, they both need to have some charge. And when you make one charge larger, then even if the other charge is still at the same size, the strength of interaction will become larger, because that's what this strength of the interaction depending on the product of charges mean. Let's see, what other information can you tell from here? There's one piece of thing that beginning physics students need a lot of reminders with, to be trained into checking and to notice it when you are not seeing it. So it's the unit. When you look at the unit, you see that force is in the unit of Newton, and the right hand side is tricky. You have different units. So you have a unit of 1 over meter squared, the distance squared. And for the charges, you will just have to know that we have a new unit of charge called Coulomb. It's technically not strictly necessary, but we work with the SI system, which has chosen to introduce this unit of charge. So the numerator there is Coulomb squared. And when you compare this left-hand side to the right-hand side, is hopefully where you see they are not the same units. So this equality doesn't work. I want to say the force is equal to something, and it cannot be equal to just this because units don't match. And that's where the Coulomb constant comes in. This is a constant, fairly large. I don't have it memorized, but I know it's fairly large. And this comes in the correct units necessary so that the units will match up. So this must have unit of Newton times meter squared per Coulomb squared. And in this unit, the Coulomb constant is pretty large. It's like, I don't know, 9 times 10 to the power of 9, or I don't have it memorized. I'll eventually have to look it up when I plug in numbers. So Coulomb's law also gives you that. So one way to say it is the Coulomb's law gives you the unit of the Coulomb constant, because this is the only set of SI units that will work out for this equality to hold. So now, what I want you to spend a little bit of time talking about is this vector stuff. I think so. I have to fess up a little bit of a bad habit of physicists and possibly mathematicians. I don't know. I only speak for physicists in me. We tend not to repeat stuff. I think a lot of times our assumption is that we say something once and that's enough, because repetition is redundant. You kind of see it in the structure of how we structure physics as a course content. We are not in the habit of making redundant, unnecessary, duplicative list of laws. It's the fundamental science, and part of something being fundamental means you need as few of these things as possible. So in the past, when I teach physics 4B, I used to not review any vector stuff. My assumption was, hey, to get here, you should have taken physics 4A. Physics 4A covers vectors, so you ought to know what the vectors are. But when we were doing thermodynamics, we didn't have to talk a lot about quantities with the direction, so vectors. So we didn't have to do that for thermodynamics. So I think as we are getting into electricity and magnetism, which probably of all the physics content that you have seen and you will see, is most directly related to the vectors in terms of mathematical operations and in terms of everything. So I think this point in the semester is the right time to do a little bit of review. So let me just start out with some visual reminder of what these arrows you see in the Coulomb's law, how they match up with something graphical. So let me talk about, for example, let's just draw example of charges. So let's say I have a charge here, Q1, and I have another charge here, Q2. And I think most people can draw, have a graphical connection with these charges in space. So you might say, all right, these two charges, they are some distance d apart, and I guess that's it. and if we weren't concerned with the vector stuff, we might say, okay, so the strength of force between these two charges is Coulomb constant times the product of two charges divided by distance squared. And and if these are both positive, for example, then the force is repulsive likes repel and opposites attract. It's a feature of Coulomb's law. Now, I want to show you a more formal description that takes into account that force is a vector quantity. It has a sense of direction, and this sense of direction matters often. So the starting place is to define a displacement vector. I think I'm calling you back to probably what might have been covered in your, I want to say trigonometry class. It might have been geometry class. Or it could have been physics 4A. So if you imagine having some space, and let me just draw XY coordinates so that I have some easy way of referring to points. This is something you do learn in either geometry or algebra 2, kind of the marriage of algebra and geometry as introduction of the Cartesian coordinate system. And with the coordinate system, you can refer to these points as with these coordinates. And vector is a mathematical object that lives in this background. And the most intuitive representation of the vector we use is this one that goes from origin to a point that illustrates the length of the vector and the direction that the vector goes in. And one of the most common letters we use for vectors like this is R. Don't really know why. Maybe for radius, if imagining this is part of a circle or something. But R is a common letter. And when we have R with an arrow on top, then we are emphasizing it's really a vector quantity with the direction and everything. So one way to represent this R vector might be in the unit vector notation. You could write this as the vector component x naught and y naught, and I'd like to represent this like algebraically, like it's these two things added together. And if I'm simply adding two numbers together, this doesn't do what I want it to do. It doesn't represent a direction. And this is where we introduce the idea of unit vector. We should have done it in physics 4A. The unit vector, for example, x hat, which other textbooks might call I hat, they all refer to the same thing. It's a vector of unit length. The length here is 1 with no other units or like meters, or it's just 1. It's a vector of unit length, vector of length 1 that points in the direction of positive x direction. And there's also y unit vector, y hat, or different textbooks might use j hat. I prefer y hat. So this is the other unit vector that points in the y direction, plus y direction. And we represented this r vector as the scalar x naught, the component, times x hat. So that version of the vector would have this length. So this would be x naught times x hat. So x hat scaled up to this length, plus y naught times y hat. So that would represent this vector, y hat, scaled up to the length of y naught, y hat. And in fact, if you remember the head to tail addition stuff for vectors, then you can see how by adding this vector and this vector, you can get your r vector. You can see graphically here. Add these two vectors, you get the r vector. So this is vectors. Hopefully all this is ringing a bell. You feel like you have seen it before. And now let me do something that to more of what we'll be doing this semester, which is that we are going to generalize, and we are going to use this notation in more context, and we are going to use it in a way that it helps reduce tedious writing. So these charges, I deliberately drew them in a kind of tilted way because if I just drew them horizontally or vertically, then they would fit nicely into one of these axes and I didn't have to do anything extra. So now that they are in some arbitrary rotation so that I can have something that's meant to be generally applicable. Let me draw a couple more diagrams or a couple more auxiliary figures. One is the definition of this R vector. So how we define this R vector? Let's say we are looking at this charge Q2 and we are considering the electric force on charge 2 by charge 1. Then the R vector that we have in mind is the vector that goes from the source charge, the charge that's exerting force, and goes like an arrow and ends at the charge that's feeling the force. This is my R vector. And as you look at this expression that's here, you don't see any R with arrow on top. You don't see this. So I need a little bit of an expansion of that. This R vector, we can break it into two parts, basically. One part that has the magnitude, that tells you how long it is, and the other part that only tells you the direction. And that's what these two pieces are. So I can write this vector this way. The magnitude R, this is a scalar, not a vector. It just indicates the length of the R vector times the unit vector R hat. And this R hat is unit vector like the X hat and Y hat before. So the thing to know is that it has length of 1. And what's special about this R hat is that it's a vector that points along R. It's a kind of a common convention. So if you have a unit vector that's pointing in the same direction as one of the vectors, then we call that vector's name and the hat. So this is how Coulomb's law is described. And here you can actually see how Coulomb's law includes this one single expression. It includes all the information you needed to know about electric interaction, the whole thing about, like repel, opposites attract. You don't need to remember that separately from Coulomb's law. Watch. Considering this charge Q2, if I have charges Q1 and Q2, if they're both positive, then I should have an electric force that points in the direction of R hat. All these coefficients are positive. So when you indicate a force on Q2 that looks like that, then that's in the direction that's repulsive, that's away from Q1. And what if you change what charge you are considering? If you change to looking at Q1, then remember how we define the vector R. It's the vector from the source charge to the target charge. Or before, when we were considering the force onto, this R vector went from 1 to 2. And now, as we are considering force on Q1, force on 1 by 2, well, so this other second R vector, it'll be originating from Q2 and then pointing towards Q1. And this would be my new unit vector for not R2. Let me label it as R on 1 by 2. So when you work out the force goes in the same direction as this R hat vector. So it goes in this direction. That's also repulsive. Now, imagine if both of these charges were negative. That possibility is already covered here. If both charges are negative, then their product is positive. So none of these directions change. They remain at the same direction. I guess that's a good thing. I don't have to do anything. Now watch what happens if one of the charges is positive. If, for example, Q1 is positive and Q2 is negative, then as you look at here, you see, okay, so this coefficient is now going to be negative. That means the direction of force is opposite of the unit vector. So if you're looking at force on Q2, and again, this is the unit vector for on 2 by 1, well, force vector, it goes in the opposite direction. So the electric force vector now has to point this way. And on 2 by 1. And this is exactly the attractive force that you might expect from opposites attract. But you don't actually have to memorize that as a separate statement or anything. This one mathematical expression contains all of that. So one of the things you will see us cover this week are the idea of electric fields. And the field idea is something that you might have seen in an earlier physics class when we cover gravity in physics 4a. We can talk about gravitational field. And there's a few different sources of motivation for introducing field. And there's a more modern reason for field, especially after you cover special relativity. The concept of field is what allows you to have a force between things in a local way without a spooky action at a distance. But that's a more modern physics reason. We don't really need to invoke that. Let me give you perhaps the most motivating reason for introducing field at this point, in this place in your physics education, and just how useful the idea of field is. So let me refer to one of the questions in your textbook. That's also one of your homework questions. This relates to this problem here. One of the questions in chapter 5 asks, here it is. So the way the question is worded here, it already refers to the idea of field. Question 83, the charge per unit length is shown, it gives the density, and then what is the electric field at point P? So, okay, this question presumes the existence of ideal field, so it doesn't quite motivate it the way I would want it motivated. So let me imagine having a slightly different question so that we can use this as a starting point for motivating the ideal field. So let's say instead of this exact question, we had, okay, charge per this, and then there is a point charge Q at point P, and none of this. And then they can be asking the question, what is the force on charge Q? And this is the kind of question you can do by the method that you see described when I do this problem in one of the videos. I break this up into small pieces. So in the video that you will see, I do it in terms of electric field, but given the connection between force and electric field, the method you use for calculating electric field, that's basically the same method for calculating the force directly. And if you're just looking at that, there might not be much of a motivation for introducing the field. It's just, tomato. It's two different ways to do the basically same thing. The incentive, the real reason to introduce the field becomes clearer when you consider potential follow-up question someone could ask here. So let's say instead of asking for force on a point charge Q, for part B, imagine someone asked this. For part B, say there is now another rod with its left end at point P. So let me just draw a version of that. So the question could specify the parameters of this rod. Maybe it has the same length as the other rod, or maybe it doesn't. But its question would specify enough of the parameters to tell you how much charge is on this rod and all that stuff. And then someone asks you the question, the following question: what is the force on this rod? This is where things get challenging. And I guess I've never actually asked this question of the class, but so given how much difficulty I see people going through working out a question of this form with the point charge, I'm almost willing to bet that if I asked this more complex version of the question, I'll have maybe one or two students in the class who can do it in any semester, not just this particular semester. And most people will think it through and maybe give it some attempt, but there will be some mistakes made in some steps and won't quite do it right. And the introduction of ideal field is a way to break up this approach so that you can do one difficult part in one way using one approach and then use the result from that to tackle other questions that someone else might ask. So with the idea of the field, what you can do here is, as the first step, you can work out what is the electric field as a function of position. And I'm not telling you that's easy. It takes, I guess it's basically similar to this answer here, except you treat A as a variable. So, so the answer you have for this electric field at point P as a function of A, you can re-express as, okay, that's my electric field as a function of X. So that's one step that takes that takes integration and detailed set of steps to work through. Once you have this expression for electric field, that packages a lot of mathematical work that's gone in. And using that electric field, now you can calculate what is the amount of force on one piece here. So some amount of force that's on some charge dq times the electric field. And I want you to note carefully how this expression here, expressing an infinitesimal amount of force, is different from this expression here. And there is a real difference in meaning here. And separating out those differences in meaning, it's a lot easier when you can actually break up problem solving into two distinct steps. And what concept of electric field allows you to do is exactly that. So when you have Coulomb's law stated in terms of forces, as we do just before introducing electric field, right here. If you are looking at Coulomb's law stated in terms of force, there's really no getting around the fact that you have to deal with a pair of charges. You have to look at interaction, force interaction. And a lot of the problem solving involving electricity and magnetism can be really simplified. We can divide it up into discrete conceptual pieces and calculational steps. If we separate this step out, one step of calculating electric field, the effect on the space around the charge due to the presence of the charge, that calculating electric field, and the second step of calculating the force due to the electric field. As in, you have one charge here that's modified the space around it, and then you have a second charge that now fills that modified space. And so for most of the semester, you won't really see us using this formulation of Coulomb's law. A lot of the times, our inquiry will be about the electric field. That's because we have this relationship in mind. Once we have figured out everything in terms of electric field, then this second step is actually really easy most of the time. So we leave that for more special applications, and we focus most of our effort in working out the electric fields. And so that's really the most direct motivation for electric field. It's a calculational tool that really helps organize problem solving. Now, as you might see in one of my other lectures, that's not the place where we will start, because the modern view is that it's the electric field that's the fundamental quantity. So I will always write this as our defining equation for electric field. We start with the field, and that gives us the force. And electric fields are real. It goes beyond the calculational tool, but we'll reserve of the ability to see that to later this semester. For now, if you just think of field as a calculational tool, that's not wrong, and that gives the most direct motivation for introducing fields and all the techniques that we'll go through in the next couple of weeks. So I want to talk about some of the almost the geometric considerations when you are dealing with the vectors. And we'll start out with the 2D. So, in physics 4a, one thing I say is that a lot of the things you do in mechanics can be done in 2D. You just pick the plane in which interesting things happen, and all your descriptions are 2D. In physics 4b, it's not really that way anymore. So when we're drawing electric field lines, then we might choose to draw it in a 2D way, because most of the things we choose to draw things on appear 2D. But when we are actually working on formulas and do like a Gauss's law based derivation that you will see next week, you will see that we actually jump right into 3D. We don't really linger in 2D. So even so, 2D is a good place to start to kind of introduce some of the ways that we deal with the things. So coordinate systems and vectors, I think it's good to kind of start out with the definition of a coordinate axis. It's a very unphysicist-like of me to start with that, because we physicists really prefer to work with vectors before defining any coordinate axis. And because some of the descriptions and calculations become easier when you have introduced the coordinate system. So let me say, I've introduced the coordinate system. Now I'm going to use this coordinate system to, for example, describe a vector that looks like this. It could be an actual vector representing position. That would be one. But actually, it doesn't have to be a vector representing position. So, this might have a length of 2 meters, for example, for position. But you can also be talking about a vector that's an electric field. And that would have a geometric representation. And that would have a magnitude of the vector that's consistent with the unit of electric field, which this week we are using so this could be 100 Newton per Coulomb. That would be an electric field vector. So for the rest of this mini lecture, we'll just say a vector is a mathematical object with a magnitude and direction. And what's important is that they have magnitude, length, and direction. There's some kind of angle you can use to describe it. And same deal here. It has some magnitude, some length, and it has some direction that you can use to describe where it's pointing. It's like an arrow. So when we are describing vectors with coordinate systems, so the most natural kind of easy one that people are familiar with is the Cartesian system, which uses the axis that I just drew. So to describe this point or this vector, I'm going to use them synonymously. To describe it in Cartesian coordinates, you would give people its coordinates. It's an x coordinate and y coordinate. and that'll be your description. And visually, you can illustrate that as, right, this is its x component, so however much that is, that's x, and this is its y component, however much that is, that's y. You've seen all that. And so Cartesian coordinates, it's nice, it's easy to grasp right away, and if with the understanding of something like a Pythagorean theorem, if you have this coordinate, you can describe the magnitude of the vector. You know, hypotenuse there is the square root of the squares, the sum of the squares of the two legs. It's very, it's useful. But especially as you will see in situation that we use, Cartesian representation sometimes leads to really complicated way of describing. And a good example is Coulomb's law. So Coulomb's law, if you have, let's say, charge Q1 here and another charge Q2 here, using Cartesian representation, this is how your Coulomb's law would appear. So for the magnitude of the forces, the electric force is the Coulomb constant times the product of the charges divided by the distance between them. Let me use d squared. Yeah, that would be the magnitude. And to describe the direction, so to describe the full vector quantity with the magnitude and direction, you have to you have to get this distance. That's going to be this quantity here, square root of x squared plus y squared. And this vector that you have at that point, you have to break it into x and y components using something that we'll talk in at more depth pretty shortly. So with all that, the description, the vector description of that electric field in the Cartesian representation, where I write down the x component and the y component separately, it's going to look like the magnitude here, k q1 times q2 divided by the distance squared. That'll be x squared plus y squared times, and I'm just going to write this down without explanation, x over square root of x squared plus y squared. That's the x component. And the y component will be k times q1, q2 divided by x squared plus y squared times y over square root of x squared plus y squared. This is how Coulomb's law appears in Cartesian representation. And I hope you are happy that we will almost never be using that. I think you might see this representation a few times when you are watching me derive electric field of an extended charge distribution using direct integration. You might see me trying to do this a couple times, but I won't expect you to do that because again, it's such an ugly expression that there are better ways to approach situations like this. So that's where we introduce a different way of representing vector quantities. We introduce the representation that you will actually see us use to introduce Coulomb's law and describe Coulomb's law, at least as an introductory thing, is going to be the polar representation or polar coordinate system. But the polar coordinate system is a little bit difficult to draw, so let me not draw it. Let me just talk about the polar representation of a vector, or polar coordinates, or polar parameters. So when you are when you're using polar representation, what you do is you deal with the two parameters. Instead of x and y components, you deal with the length, the magnitude, and direction. It's like it naturally fits in with how we define vectors, the properties that vector has. So in describing this vector in polar representation, the first quantity you would have is the distance r from the origin where the tail of the vector is to the tip where it indicates the length of the vector, and an angle theta. I guess I already labeled the theta. So this r and theta that might even be called your polar coordinates. And you can kind of imagine how with these two parameters, you can describe any point in this entire two-dimensional plane. If you had a point here, for example, you would have that distance r, r2, and you would have this angle all the way from here to here, theta 2. And if you wanted to describe a particular point to someone else, you can measure with the ruler and protractor what that length and direction is. And in the polar representation, Coulomb's law looks super beautiful. In the polar representation, Coulomb's law looks like it's still going to be a vector law because it describes a force, and it'll look like the magnitude length, which will be Coulomb constant times product of the charges divided by, let me use the letter r, distance between the source charge and the force charge that's filling the force. That'll be r squared. And this is the magnitude. I have to turn it into vector. Within the polar representation, there are two unit vectors. Let me kind of take this point and just blow them up here so that I can draw a large picture. The two unit vectors in the polar coordinate system, it looks like this. So I had this radial line coming in. I have a radial unit vector, r hat. It goes in the direction of the r. And so you need two orthogonal unit vectors to define a coordinate axis, and your second, the unit vector that's perpendicular to this, is your theta hat unit vector. And theta hat, it kind of goes in the direction that theta increases. So if you had a circle, it's a tangent to the circle, and it goes counterclockwise for the two-dimensional thing. So with the Coulomb's law only points in this direction. So we would say this magnitude in the direction of r hat. This is Coulomb's law in polar representation. Much simpler, more beautiful. If we could, we would just stay in polar representation and work everything out using polar representation. Nah, we can't. So there are some scenarios where you do have to actually work with a Cartesian way of dealing with the things. So without going into too much of a detail, because I do want to finish up kind of describing the coordinate axis and how to relate them, let me just give an example. An example of such a scenario where it's difficult to stay 100% in the polar coordinate system is an example of a dipole, which you will be seeing more of. In an arrangement of charges, positive charge here and a negative charge here, if you, for example, want you to figure out what is the net electric field here, then in order to figure out what's the magnitude of electric field due to the or what's the influence of the electric field due to the positive charge, and what's the influence of the electric field due to the negative charge. And as you are doing all that, you kind of deal with the Cartesian aspect of it, because you have this displacement between the two charges that are along one of the axes, kind of set up in a Cartesian way. So let's just go over how you convert between a Cartesian system of coordinates, Cartesian system of parameters, coordinate variables, and the polar system of coordinate variables. So let me have this example in mind. So this example here of, let me just pick a point. In fact, for sake of variety, let me pick 2 points. This is going to be my point 1, and this is going to be my point 2. And you can think of how one might describe it with the Cartesian coordinates. That's the kind of the natural one, x and y. You could say, oh, x and y, that's my coordinates. And I want to describe its polar coordinate. And the polar coordinates, I think once you draw the picture, you will begin to see. So for the polar coordinates, what I need is, I need this distance here. And I need this angle here. If I have theta and r in terms of x and y, that will give me how to convert to polar coordinates from the Cartesian parameters. So as you look at it, the kind of the thing that I hope you will get into practice of noticing is, I want you to notice the right triangles. because the right triangles will allow you to use your trig knowledge. Reminder of the so, ka, toa mnemonic that you've learned, which stands for sine is, so sine of an angle is the opposite over hypotenuse, and the ka is cosine of the angle is the adjacent over hypotenuse, and toa, the tangent of an angle, is the opposite over adjacent. These are the initials that I'm using. So, and the angle that it's talking about is always an angle of a right triangle. So I have this right triangle here. So, so as I look at it, so by knowing my Cartesian coordinates, what I do know is I know the two legs. I know this is x. I know this is x. I know this is y. So I can use Pythagorean theorem that tells me the hypotenuse. R squared is equal to x squared plus y squared. Or if I want pop r, which is a positive quantity, then r is the square root of x squared plus y squared. That part I actually didn't need any trig functions. The trig functions will be needed for the next part, where I try to figure out what's my theta. So in order to get, and that's where I know this, my theta occurs in all these functions. So I must be able to use something here to figure out theta. Good? And actually you have three different ways to get at it. You could actually, having already figured out the hypotenuse, you could say, all right, I have the opposite side, y, so I can say sine theta is y over square root of x squared plus y squared. So my theta would be arc sine of y over square root of x squared plus y squared. That's not wrong. Most times you will get right answer. I just want to represent the kind of the shortest pathway of converting from Cartesian coordinates to polar coordinates, which would be, so in order to write what I just wrote, you actually kind of had to figure out the hypotenuse first. And suppose in whatever scenario you are in, you either don't know it or you don't want to figure it out. Then what you should consider doing is use only the parameters that are directly given to you in the specification of the Cartesian coordinates. Then you could say, I have this leg here, which is opposite to the angle. I have this leg here, which is adjacent to the angle. If I use the tangent, then I can do that. So if I write down tangent of theta is equal to opposite, that would be y over x. So you say, to find the angle itself, you apply arctangent through, and you say theta is equal to arctangent of y over x. You could almost call this the formula to convert from Cartesian to polar. Now, if I stop there, I'll have told you something that's not 100% correct. There's a slight bit of an issue. Not with this step. This step is actually perfectly fine. But this step here, if you get into habit of using that, sometimes you will make mistakes. So let me just point that out. I can point that out with this point here. Let me just be concrete with that point. Let me give it some numbers. Its x component is -5. Its y component is 3. So, so you go through this. Okay, I want to figure out what is my the magnitude r. So you say r is equal to square root of -5 squared plus 3 squared. I do not believe I can do that in my head. So let me use a calculator. -5 squared is 5 squared. So I do 5 squared plus 3 squared is that. Take the square root, 5.831. That's my magnitude. Good. And you move on to the next thing. Okay, let's calculate theta, which is going to be the arctangent of, let me write it out first and then plug it in. It's going to be arctangent of minus 5. Wait, no, that's not right. The y coordinates, that would be 3. 3 divided by x minus 5. Okay, so on my calculator, I have to start with what's in the arctangent. So 3 divided by 5 minus sine, minus 0.6 looks right. Okay, let's do arctangent. Second, inverse tangent. And it tells me, okay, minus 30.96 degrees. I think I'm in degree mode. And I hope you can obviously see that when I draw the angle of minus 30.96 degrees, that doesn't give me the direction of my actual vector, which is going in this direction. This is something you always have to be careful whenever you are using inverse trig function. It comes down to, because imagine looking at a plot of sine of x or cosine of x, or tangent of x, but tangent looks kind of ugly, so let me just plot out as a function of theta, sine, and let me do cosine in blue. So sine curve looks like this. Over a theta of 2 pi, from 0 to 2 pi, sine looks like that. Cosine over a period of 0 to 2 pi looks something like this. Oops, wrong color. Cosine is going to be blue. Cosine over a period of 2 pi looks something like this. And the problem is, so the functions themselves, these are fine. You pick a value of theta, there's going to be a single value that corresponds to whatever the sine of theta is. You pick a value of theta, there's going to be a single value that corresponds to whatever cosine of theta is. Sometimes positive, sometimes negative. The challenge is, imagine trying to do a reverse lookup, where someone gives you the cosine or the sine and asks you for the theta. There's going to be, so for a given value of sine theta, for example, there's going to be a multiple theta that meet that condition. There's going to be one theta here that meets that condition. There's going to be another theta here that meets that condition. So when they define the inverse trig function for your calculator, they deliberately limit the range of those inverse trig functions. So for arcsine, the output of arcsine, whatever ratio you put in, it's always going to be between, in radians, minus pi over 2 to pi over 2. Meaning, when you use arcsine, the answers you can possibly get are only in this range. In the language that we use in geometry trig class, either quadrant 1 or quadrant 4. And if you are using arc cosine, that's and again the input being some sort of ratio, it's always going to be limited between, I want to say, 0 and pi. So it's going to be limited between something in the first quadrant or the second quadrant. And finally, when you have arctangent, it'll, for whatever ratio you put in within I think with arctangent, the domain is all the real numbers. Then the smallest value it'll give you is minus pi over 2. And the largest value it'll give you is pi over 2. So that's why we got this value. In degrees, it gave me something between 0 and minus 90 degrees. That doesn't mean that your actual angle that corresponds with this ratio of y over x is actually in the fourth quadrant. As it's drawn here, it might be in the second quadrant. So, so as far as converting from Cartesian to polar coordinates go, I prefer to not have this final formula because it's a little bit misleading. You might use it, but you have to be careful when you use it. Instead, I prefer to just leave it here. This expression will always be valid. So, when I take the ratio of the y over x, when I take the ratio of 3 over minus 3 over minus 5. That ratio is actually correct. So for that point, if I, so whatever this angle ended up being, if I, it is going to be correct that if I calculate tangent of that angle theta that I've drawn there, then that ratio is going to end up being what we calculated here, minus 0.6. Minus 0.6. So that is actually going to be correct. And let me actually demonstrate. So having seen this angle, I actually can figure out what this angle theta will be. That angle theta will be 149.04 degrees. So if I have the angle 149.04 degrees, and if I take the tangent of that, I do get the correct value. Minus, something that's close enough to 0.6. So what you have to do here is you have to kind of work out what quadrant, quadrant 1, 2, 3, or 4 your vector actually is in, and use that to inform what angle theta your actual angle will be. All of this is done much easier by drawing a figure. So that's how you should do it. And converting from polar to Cartesian, sorry, this took a long time. So I think I'm out of time to do polar to Cartesian. I'll reassess how much of this I want to do in the future. I'll just give you the formula. So the formula to convert from polar to Cartesian, that is actually a lot easier, and it doesn't have as many caveats associated with it. So with the polar, so the assumption is you've been given r and theta. You know the magnitude and the angle. Then the x component, x component should be r cosine theta, and y component should be r sine theta. This kind of, this is the kind of thing I was trying to discourage in my physics 4A, automatically associating cosine with x and sine with y. But as far as the conversion formulas go, cosine gives you x, sine gives you y. Because of the way it's defined, the angle theta is defined to be angle from the positive x-axis going counterclockwise. So that's the formula, and there's fewer things you can do wrong with it. And I guess I didn't quite get to 3D. I might find an opportunity to cover 3D coordinate systems, which is the two kinds that you might have seen are the cylindrical coordinate system and the spherical coordinate system. And if there's an opportunity in the future, I'll try to cover that.